Boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to The Naked Scientists with me, Ben Valsler, and with Helen Scales.
Hello.
This week we're exploring the science of ageing. Coming up, we'll find out how your DNA changes and becomes damaged as you age, and how understanding DNA repair could keep us going for longer. We also find out how to keep our skin looking fresh and young into old age, and the simple lifestyle changes we can make to have a longer, healthier life.
And we'll be finding out how high bees can count. And yes, that's right, even though they don't have any fingers to count on, bees can actually count. We'll also be finding out how an extinct species of giant tortoise may actually not be lost forever. And we'll also discover how gene therapy is helping blind people see again. And also a way to get more miles out of a single tank of diesel.
And Dave and I bring you the stretchy science of rubber bands in our kitchen science experiment, playing with liquid nitrogen to find out how elastic responds to temperature.
And Diana O'Carroll will join us for a hair-raising question of the week.
Why is it that eyebrows tend to grow quite long in elderly people?
That's all coming up in today's Naked Scientists. So if you want to get in touch with any questions or comments for us, we would love to hear from you. You can email us on chris@thenakedscientists.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, first off, news from the world of medical science, with this week researchers who have taken a step closer to using gene therapy to help people with blindness see again. Arthur Sidisian from the University of Pennsylvania led a team who've been looking at therapies that aim to help people who suffer from Leber congenital amaurosis, or LCA, which is a rare inherited form of blindness. And essentially, studies in animals have shown that what's causing this disease is a mutation in a particular gene called RPE65, which messes around with something called the retinoid cycle, which is essentially the part in your eye where vitamin A is regenerated, and it's the key part of essentially converting light that hits your retina into nerve signals that are sent to the brain. So when this mutated gene is inherited, it knocks out part of that cycle and vision is impaired. Now, they've been using gene therapy to replace this RPE65 gene in animals, and they've actually been very successful in restoring vision in laboratory mice and things like that. The way they do this is by using a genetically modified virus, an adeno-associated virus, which is injected into the eye, and essentially it delivers a good version of that faulty gene so that it fills in that missing part of the retinoid cycle and brings vision back. Now, the good news is that they've started trying this out on people. Now, these are just really early stage clinical trials, but they've already shown that the treatment is safe to use and it can lead to a moderate improvement in vision. Now, 3 patients with LCA were injected with the treatment, and after 30 days, all 3 of them had shown quite an improvement in their eyesight. Now, it seems the therapy is increasing the activity of cone cells, which are the part of the eye responsible for seeing colour, by up to 50 times, and that the activity of rods, the parts of your eye that are responsible for night vision, would actually increase in their activity by 63,000 times, which is amazing. But while this is really encouraging news for people with this condition, the results are actually still far from perfect. One real problem is that the patients took a very long time to get accustomed to the dark. You must all be familiar with how long it takes you to get used to sitting in a darkened room, and after a while you can see things that you couldn't before, and that's your eye adapting to the low light levels. And in people with normal vision, that takes about an hour, up to an hour. But in these people with the people who've taken this gene therapy, it can take up to 8 hours. So it is happening, but very, very slowly in these people. So it might not be perfect, but it certainly holds some hope for the future that this can be developed for people suffering from this inherited condition.
Fantastic. Well, it's good to hear that we have various treatments coming up, because not too long ago, our own Mira Senthilingam was reporting on a stem cell patch for people with macular degeneration. So it looks like there's a lot of good work going on into making blind people be able to see again. Now, I don't have this problem because I'm a cyclist and I don't have a car, but it does seem that if you drive a car at the moment, regardless of whether it's petrol or diesel or whatever you're putting in, it's costing you a lot more money than it used to. But it now looks like subjecting your diesel engine to a strong electric current could actually improve the efficiency by about 10%, which could save you a great deal of money. Internal combustion engines are getting more efficient with each generation of cars, but we're still a very long way off them being perfect. But now researchers at Temple University in Philadelphia have found a way to make diesel engines more efficient by making the droplets of fuel injected into the engine much smaller. Now, a diesel engine works by spraying a fine mist of fuel into a chamber where the pressure of a rising piston causes it to explode. It burns. And when it burns, the fuel and its products massively expand, and the expansion of gases pushes the piston back, and that powers the vehicle. Now, the smaller the fuel droplets are when they're sprayed into the chamber, the more efficiently the fuel can be burnt, and so the more miles you'll get from one tank of fuel. Writing in the journal Energy and Fuels, Ronjia Tao and colleagues report on an electrostatic device which could be fitted to a standard engine and subjects the fuel to a strong electric field shortly before it passes into the fuel injector. They call it an atomizer, just like you have with perfume and aftershave. Now, this gives each droplet of fuel a negative charge, and because like charges repel, the droplets then repel one another and form a finer mist as they're sprayed into the combustion chamber. That makes the engine more efficient and improves the fuel mileage considerably. They've shown it works well on 2 engines so far, and they're confident it can be adjusted to work with existing engines as well as new ones, but also engines running on diesel or petrol, or even things like biodiesel or petrol mixed with ethanol, or even running on kerosene. So it's very promising.
I take it that the level of electricity needed for that isn't going to actually outweigh the efficiency of because you said it was a very large electrical current needed. It can't be that much, I take it.
Well, it's a fairly strong current in a fairly strong electric field in the area where it's implied, but actually it runs on something like 0.1 watts, so it's a very low energy consumption, which was something they were worried about and something they've managed to get round.
Awesome. Well, it does seem like we need anything we can to help improve our efficiency in life at the moment. But I'm going to hop across to the world of the animals now. This week saw the return of Galapagos Day, which is an annual event held by the Galapagos Conservation Trust. And this year there was some good news, which is a species of giant tortoise that was thought to have gone extinct over 100 years ago might in fact not be lost forever. Now, a team of scientists from Yale University in the States have extracted traces of DNA from specimens of extinct Galapagos tortoises, which are kept in museums. And they've discovered that a species that used to live on Floriana Island, which is one of the Galapagos Islands, is actually genetically distinct from all the other ones that are still around. Now, those results, which were published in the PNAS journal this week by Giselle Ciccone, you might think they're not that groundbreaking, that yes, a species should be different from all the others, but the exciting part of their study is the fact that some of the other tortoises that are still alive in the Galapagos are actually turn out to be close relatives of those ones that went extinct on Floriana Island all those years ago. Now, in fact, the Floriana Island tortoises were thought to have gone extinct within 15 years of Charles Darwin's visit back in 1835. And it was these giant tortoises which were one of the things that really got him thinking about the theory of natural selection and evolution and so on. And it's not just because these things grow to a ton in size and can live for over a century, which I think would get any of us thinking, but it's more the fact that he noticed that on different islands there were different types of these tortoises, and that got him thinking about the way they're changing in different environments that are isolated from each other. But sadly, partly because of their great lumbering size and lack of speed, these tortoises really have suffered at the hand of man, and 4 out of 15 of the species are now extinct, including the Floriana tortoises. But what Ciccone and her team have discovered is that the tortoises living on Isabella Island, another one of the Galapagos, as I say, are relations of the extinct Floriana species, which they think actually what happened was probably a few of the Floriana tortoises found their way to Isabella, maybe even because whaling ships, which was one of the real reasons why these tortoises went extinct, was because the whalers ate them and took them with them when they needed to go back overseas. Perhaps they thought, we've got a few too many tortoises, and they dumped one off on Isabella. And they actually interbred with the Isabella tortoises. And so, in fact, half of the genes of the Isabella tortoises are actually the Floriana genes, so they're living on. So what does this mean? Maybe there is a possibility that we could bring back the Floriana tortoises. There could be a way of captively breeding the living tortoises and get rid of the Isabella genes, if you like, until they just entirely contain the Floriana genes. But should we be doing that kind of thing? I mean, I think obviously it's a very important thing to think about animals going extinct and the ways that humans are affecting that. And obviously the tortoises are particularly special because of the influence of on Darwin and so on. But it seems like an awful lot of money to think about spending on one species when there's so many other species that haven't yet gone extinct that maybe we should be spending our money on. So I don't know, but I think at least it opens up the possibility that maybe extinction isn't forever. But I think really we have to think about the fact that we have to stop so many things going extinct in the first place.
Very true, yes. Well, a species that have surprised us recently is, in fact, honeybees. And it seems that honeybees are capable, we know they're capable of finding nectar. We know they can tell other bees where to go through the medium of the waggle dance, which is a beautiful thing to watch. But now, scientists at the Australian National University in Canberra have shown that bees can actually count up to 4. Writing in the journal Animal Cognition, Mary Dacker and Mandyam Srinivasan tested the bees' ability to count by training them to receive a reward, some food, after passing a specific number of landmarks. Now, they changed the distance between the landmarks, so the bees weren't just learning the distance to the food, but specifically the number of landmarks that they must have passed. Now, interestingly, they were capable of counting landmarks that they had never encountered before, so even if they changed what the landmarks looked like, it was the number of landmarks that was important. Now, that shows that they're capable of transferring the count to a novel object, so in other words, they can count an object regardless of what it is. They tested the bees' numerical abilities using a tunnel placed 7 metres from a hive. It was 4 metres long, 20 centimetres wide and 20 centimetres high, and they placed identical landmarks along the tunnel initially, and they hid a food reward behind whichever landmark they chose. They kept varying things so that the bees weren't just learning, instead they had to actually count. And they changed things so that the bees could only see one landmark at a time. This means they must be aware of how many have come before the one that they're on in order to know where they need to go now. So they must keep a mental tally. Now, furthermore, although the experiment shows that bees could count up to 4 landmarks, interestingly, it fell down dramatically after 4 objects. In fact, bees can count up to 4, but not count up to 5.
But they haven't got any fingers to count on anyway, so I know we can count to 10.
That's very true. We can count to 10 and possibly even a little bit further. Now, also in the news this week, researchers at the Howard Hughes Medical Institute at Caltech have followed an antibody as it passes through the wall of the stomach. Now, this must happen for a mother to pass on immunity to a baby through breast milk. In order to see what happened, they attached nano-sized particles of gold to antibodies that they then fed to rats. Now, Professor Pamela Bjorkman was leading the work and joins us now. Hi, Pamela.
Hello.
So, Pamela, how did you actually do this? How did you see these antibodies passing through the stomach wall?
Well, first we used a technique called electron tomography. So normally electron microscopy, you take images of cells and you see their organelles that you can usually achieve nanometer resolution. So you can see membranes and other things like that. But by attaching the nanogold particle to the antibody, we could trace it as it was taken up by the intestinal cells, and we could watch which parts of the inside of the cell it progressed as it was going across the cell.
Now, a lot of the time with these sorts of experiments, people use something like a fluorescent tag which they attach to whichever chemical they're trying to follow. Would this have been possible, or is it vital that you use this nanoscale gold?
A fluorescent tag wouldn't be visible in an electron microscope because what you need to see there is very electron-dense particles. So the gold tags we were using were actually 55 or 60 gold atoms that were actually attached, and that is electron-dense enough that with a little bit of an enhancement procedure, we could see those. So every time we had a transport event, we could visualize that by one of these gold tags. So we were actually looking at a single receptor bound to an antibody in each case, and it was visible by the gold tag.
So once the antibody binds to the receptor, how does it get through the cell? How is it pushed through?
Well, it comes in through what's called receptor-mediated endocytosis, so it binds to its receptor, which is on the side of the intestine that faces when milk comes into the gut, and so it binds there. It goes inside the cell into these membranous compartments that are like little, they're very strange shapes, but they're tubes or they're like big spherical balls. So it goes inside those, and those are acidic. And this receptor binds very tightly to the antibody at acidic pH. So these vesicles wander around inside the cell, and then when they reach the side of the cell that faces the bloodstream, which is where they eventually want to dump their cargo, these little tubules fuse with that membrane, and then they're exposed to the pH of blood, which is slightly basic, and at that pH the antibody rapidly falls off, enters the newborn's bloodstream, and the result is that it acquires its mother's antibodies.
So it's the difference in pH between inside your gut and inside your bloodstream that actually makes this a one-way process?
Exactly.
And so why is this so important? Why do we need to transfer antibodies from breast milk to blood?
Well, it turns out that human babies don't develop a fully functional immune system until later, and it's very helpful to them to have some of their mother's antibodies. So it's like a passive immunization. It's like the mother vaccinates them with antibodies against whatever pathogen she encountered in her environment, and that's directly relevant to what the baby will experience. So it's been immunized by its mother.
And could this be the same mechanism through which things like HIV are transferred from mother to baby?
Well, HIV is transferred through breast milk, that's true. But actually, there's a little bit of a technicality here. Most of the types of antibodies that are in breast milk are not the types that are transferred by the receptor we were studying, in human breast milk anyway. So we were studying the transfer of IgG antibodies, and most of the antibodies that are in human breast milk are IgA. So rodents transfer IgG through breast milk. Humans transfer IgG before birth, mostly across the placenta. So much of the antibodies that humans acquire is before they're even born. It's by a transfer across the placenta. And then human fetuses swallow amniotic fluid, and it's possible that they transfer maternal IgG to their bloodstream through the swallowing of this amniotic fluid that contains the mother's antibodies. But I don't think that humans actually transfer, human babies don't acquire HIV through this mechanism.
Okay, fantastic. Well, thank you ever so much, Pamela. That was Professor Pamela Bjorkman from Caltech explaining how you can use gold, or tiny particles of gold, to shine a light on biological processes.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists with me, Helen Scales, and Ben Valslow.
Don't forget that we beam this programme live into Second Life, the virtual world of Second Life, every Sunday from 6 p.m. UK time, which is actually 10 a.m. in Second Life. There's a fantastic group of avatars there who discuss the science in the show, so a big shout out to all of you there. And if you'd like to join them, visit the Scilands area in Second Life and just do a search for The Naked Scientists. You can drop by our mansion, relax on one of our sun lounges and listen to the show. Whenever I'm not here, that's where you'll find me. And while you're online, why not tell us how we could make our show even better? We really want to hear from you about what it is that you like about what we do or what it is that you dislike. So we've set up a survey at thenakedscientist.com/survey.
It's now time for this week's Kitchen Science, where Ben, Valsler, yes, and Dave are looking into the stretchy science of rubber bands.
For Kitchen Science this week, Dave has brought me down to one of the labs at the Department of Pathology at Cambridge University. But the thing is that with Dave here, it doesn't look so much like a lab, although we do have liquid nitrogen. It looks a little bit like a garage because we have a DIY-style heat gun, and a little bit like a stationery cupboard as we have a big pile of elastic bands. So Dave, what are we doing today?
We'll be looking into some of the properties of rubber when you alter its temperature.
So that ties in with today's show because we know that when you age, your skin becomes less elastic. So now we're looking at the properties of elastic.
Yeah, that's right. I've got a whole selection of rubber bands here. I've got a couple of them identical. What I'm going to do to start with is hang one on a little hook here.
Okay.
Now, if you take an elastic band and stretch it, it's quite easy to stretch to start off with, and then it suddenly gets very difficult to stretch anymore.
Yes, okay, because after a while, it really becomes quite difficult. It starts to sort of cut into your fingers a bit.
That's right, it gets much, much stiffer. We want to weight this elastic band until the point where it just starts getting stiffer. So I've got a load of bits of metal, which I've worked out to be about the right weight for that, so I'll add those. Okay,
and we've put that on, and it stretches the elastic band down. It does look like it's under quite a lot of tension, though.
Yeah, we probably need a bit more weight before it breaks. What I'm going to do now is heat that up and cool it down and see what happens to the length of the rubber band.
So what are you going to heat it up with?
That's quite easy. I've got a hot air gun that you use for stripping paint, but a hairdryer would work fine.
OK, and once we've done all the heating, how do we cool it back down?
Well, you could do that by just putting it in a freezer if you're at home. But seeing as we're in a lab and we have access to it, I'm going to use some of the vapour coming off liquid nitrogen. Now, liquid nitrogen is a liquid at minus 200 degrees centigrade, so the vapour coming off it is going to be very, very cold. So I'm just going to pour some of that vapour over it and let it cool down gently.
So we're looking at the properties of elastic, but what do you think will happen when we heat up and then cool down an elastic band with a weight on the end? Will the elastic band stretch? Will it snap? Or will it do nothing whatsoever? We'll show you what happened to our elastic band later on in the show.
And we'll be back later on in the lab to find out.
But if you think you know what will happen to our hot rubber band or our cool rubber band, or if you want to get in touch with any questions or any comments, we would love to hear from you. The email address is chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
You are indeed listening to The Naked Scientist. Now, this week we're talking about the science of ageing. And as we know that as we get older, our bodies become less able to tackle with infections, they become slower to heal and more prone to diseases like type 2 diabetes. But many of our individual cells that make up our bodies are constantly replaced as they divide and multiply. So why don't we feel as young as our youngest cells? The answer could be the damage that occurs to our DNA due to exposure to radiation or toxins, or just the copying errors when our DNA is replicated. Now, Professor Steve Jackson joins us now from the Gurdon Institute at Cambridge University. His team are trying to understand better how DNA becomes damaged, how this damage relates to disease, and how to repair damaged genes. Hi, Steve. Thanks for coming on The Naked Scientist.
Hi.
Now, so how does DNA become damaged in the first place?
There are a tremendous number of ways that DNA can be damaged. We're all aware of the fact that if you sit in the sun too long, the ultraviolet light can damage DNA. Certain chemicals can. Radiation used, for example, for radiotherapy can damage DNA. But actually, the largest source of DNA damage is oxygen. About 1-2% of the oxygen we breathe actually gets converted into things called reactive oxygen species in the mitochondria in our cells. Some of that escapes. That, together with hydrolytic reactions catalysed by water, is occurring all the times in our cells, even if we're sitting in the dark away from everything else, not being exposed to any chemicals. The amazing thing is that we have around 10 to the 14 cells in our bodies, and every cell in our body is sustaining around 100,000 lesions per day. So our bodies, if you're not sitting in the sun, you don't have to expose yourself to any other chemicals or anything, is having to deal with somewhere in the region of 10 to the 18 to the 10 to the 19, that's 18 or 19 zeros after 10, lesions per day.
Is that lesions in the DNA?
That's damage to DNA, yes.
That's damage to the DNA. Right, and so our DNA is, as you say, being damaged all the time, but why does this now lead to disease?
Well, fortunately, the vast majority of that DNA damage gets detected very rapidly by certain specialised proteins in our cells and gets repaired. So the vast majority of that DNA is repaired, but some of it isn't. It escapes these surveillance pathways. That damaged DNA, when it is eventually put back together again, often has errors. They're mutations, and those mutations can mean that the cell isn't working in the way that it quite should.
And you mentioned the surveillance. Now, this sounds like we've got something fantastic going on in our bodies to try and undo this damage that's happening to us on a daily basis. So how can we naturally repair our own DNA? What's going on inside the cells?
Well, if we didn't have these surveillance pathways, we wouldn't last very long. The fact is that most of the DNA damage that's occurring is repaired. And what my lab and other labs in this area are working on are trying to understand how these molecular policemen work. And really, they are molecular policemen. They're proteins that patrol the cell, looking around for damage, not doing very much, but when they stumble across damage, as it's occurring all the time, they jump on the DNA, send out signals for the cell, alert signals for the cell to stop doing things such as dividing while the damage is there, and then hopefully repairing that DNA damage in a way that doesn't generate mutations. And as I say, these pathways work very well, but occasionally they go wrong, and that can lead to mutations that can contribute to diseases such as cancer, and we believe it can also contribute to ageing.
You mentioned also, you touched on the idea that we might be able to do something like use these mechanisms of repair ourselves and actually, promote that kind of repair. Is that something that we're actually seeing happening already, or is this just still ideas of being able to mimic those natural repair mechanisms? I
think ultimately it should be possible to find ways of improving these surveillance, these repair mechanisms, and if we could find ways of improving them, I'd place a bet that it would actually slow down at least some aspects of ageing, maybe not all of them. The problem is our cells are working very, very efficiently already, so finding a way to actually make them work better is difficult. But I think one very interesting idea is that many pathways, just like the police forces, other surveillance systems, can work in a latent capacity or can be induced. And there's a growing body of data now showing that a little bit of stress to the cellular systems can hyperactivate these repair pathways. So I think one of the major opportunities might be finding ways of boosting our defense systems by making our cells in this higher state of alert. And I think if we could do that or find drugs or other ways of bringing that about, then that might actually slow down aging at the cellular level. So we're sort of, if we can tease our cells into thinking there's a little bit of damage going on perhaps, or mimic that at the effect of a bit of damage, then cells might actually kick in that repair mechanism and help repair the damage to the DNA. Absolutely. And I think even some things that we know might contribute to slowing down aging, at least in some regards, such as exercise, might be exerting some of their influences by stressing our cells. And we know that stress from work in my lab and other labs tends to induce these DNA repair and other pathways.
So a little bit of stress might be good for us.
That's what I keep saying to my students, yes.
It's good to keep us going. So do you think we could ever actually stop ageing altogether, or is this something that's just such an inherent part of life that we're never going to actually overcome the fact that the DNA suffers so much damage as we live our daily lives?
I think it's going to be very difficult to find ways of reversing aging, even stopping it, because as I pointed out earlier on, much of the DNA damaging chemicals are things such as oxygen and water, which are intrinsic to life. It's very difficult to have a system that's 100% accurate in terms of repairing damage. Having said that, we know that different mammals can live tremendously different lengths of time. So it is possible for an organism to develop in a way over evolution to live much longer or live less long. And I think if we understand all these pathways and also understand why some organisms live longer than others, we might be able to find ways of tweaking the system to make us live longer.
And if it isn't maybe just a case of living longer, but perhaps improving certain parts of our lives, is there anything in particular that the damage to DNA, apart from obviously the diseases, are there any other aspects you think that we could really work at towards improving through maybe mimicking these repair mechanisms? If it's not just in terms of, well, I've got a few wrinkles and I'd rather not have those and I'd rather live for longer. Are there other aspects of ageing in the body that are really the crucial things that we would want to look at, do you think?
Right. I think it's very easy to think about ageing as a superficial thing, such as greying of your hair or wrinkling of your skin. But the reality is, ageing has a range of diseases associated with it, and that's neurodegeneration, cardiovascular disease, and cancer. We know from work in a number of labs, including ours, that defects or problems with these DNA repair mechanisms can lead to cancer. We also know that they can lead to neurodegenerative disease, and there's growing data suggesting it can contribute to cardiovascular disease. So I think ageing shouldn't be thought of as a superficial issue. Ageing occurs in our organs and in our brains, and I think those are the kind of diseases that we might be thinking about alleviating.
Fantastic. Thanks, Steve. That's Professor Steve Jackson from Cambridge University explaining how stopping DNA from getting damaged could lead to longer, healthier lives.
Laying the facts bare. The Naked Scientists.
Now, we all know that getting all the right vitamins and the right minerals are very important for our growth and development, but they can help us stay healthy once we've finished growing as well. Now, some vitamins, such as vitamin A, can actually help us retain our youth by helping our skin lose its wrinkles and look a bit younger. We sent Mira Senthilingam out to find out more about our skin and how it's possible to reverse the effects of skin ageing.
Whilst ageing is both a physical and psychological process, when many of us think about getting older, we think of wrinkly, sagging skin. So this week, I'm in Brentwood, Essex, in the home of Dr. Patrick Bowler, Fellow of the British Association of Cosmetic Doctors, to find out just what happens to our skin as we age, and if, as all the cosmetic companies promise, it's possible to reverse the effects of ageing.
The skin is the largest organ of our body. So we have a base layer called the dermis, in which there are blood vessels and fat and nerves. And then there's a very important layer above that, the epidermis, which produces new skin cells constantly. And these cells make their way to the surface and shed off over a period of a 28-day cycle, something like that.
So what happens to our skin as we age?
There are many factors that cause our skin to age. There's a genetic factor, and then there's environmental factors, which are probably the most important. But there are a number of changes that go on in the skin. The skin becomes thinner. So if you took an extreme of a lady in her 80s or 90s, if you look at the back of her hand, the skin's almost translucent. You can see the blood vessels. We get pigment changes, age spots. And the elastic, it's a bit like the cement between bricks. The elastic tissue and the foundation of the skin also starts to reduce in strength. And that is part of the problem in developing sagging skin and wrinkles. So the supporting structure of the skin starts to become less elastic.
So I can imagine that a loss of elasticity can cause the sagging, because it obviously will keep it less taut. But what about the wrinkles? Why do they happen?
Well, there are different types of wrinkles. So if you looked at the forehead, for example, or around the eyes, where there's a lot of muscular movement, the muscular movement plus damaged, aged skin produces wrinkles. But as we go further down the face, say, for example, the cheeks and down into the jawline and the neck, that's more due to loss of volume in the skin, so we lose fat and elastic tissue. So we get sagging, and in that sagging you get wrinkles. It's a bit like letting a balloon down quickly, you're left with that crinkly appearance.
Well, in our society today, there's a wide range of products out there that people are resorting to in order to try and reverse these effects. What are these ingredients that are being used in the creams that are purely targeting people that are wanting to reverse their ageing?
We had, about 25 years ago, a big breakthrough in skin treatments when a form of vitamin A called a retinoid was actually shown to reverse some of the signs of aging. That's pretty miraculous for that to actually be proven scientifically. But it was in a very strong form of vitamin A, which was quite irritating. But at that time, the cosmetic companies jumped up and down and thought, yes, this is fantastic, we'll use this. So they developed ingredients derived from vitamin A, which are basically vitamin A but different types. Most of them are weak because if they increase the concentration, they become irritating. And unfortunately, you've got to increase the concentration for them to be effective in a true anti-aging effect. So all the vitamins that you see in over-the-counter products like vitamin A, C and E, they're the common ones that we see, are going to have positive effects, but they're not going to be true anti-aging effects.
So is the true way to have an anti-aging effect then to irritate the skin and then cause the skin to regenerate?
With vitamin A, that is the case. The concept of irritating the skin on the surface makes the cells underneath react and produce newer, younger, fresher-looking skin cells, if you wish. But in a single skin cell, and this always amazes me, there are something like 10,000 receptors for vitamin A. So when vitamin A locks onto this receptor, certain things trigger off in the skin, which affect cell division and other complex chemical cycles that go on. The vitamin A, the retinoids in particular, have also been shown that they can stimulate collagen production in the dermis. And this is very important because one of the effects of aging skin is that we lose collagen, lose volume. So if we can replace that in some way, that's going to have a true anti-aging effect. So, in summary, it's not just the irritation. There are some more profound things going on deeper in the skin and in the cells that we don't really understand just yet.
What if people were to just increase vitamin A in their diet as opposed to applying it to their skin?
Vitamin A, in particular, if you take it orally, can be toxic if you overdo it. It can affect the liver and have quite serious effects. So I would usually advise my patients in this instance that it's good to treat the skin inside and out. So to apply creams containing vitamins superficially, and also to make sure, A, you have an adequate diet, and if you don't think you have, to take a vitamin tablet as a sort of fail-safe, as an insurance policy, really.
What should people be doing in order to just help their skin in the long term and just try to not maybe have to resort to creams?
For most things, moderation is the key. However, in looking after your skin, there's one thing that's really important, and that you have to be very careful with the amount of sun exposure that you have. To have in your moisturiser a sunscreen is probably the best tip that I can give you to keep your skin looking good.
So keeping your skin protected from the sun could mean you don't need to resort to all those anti-aging creams and potions to look youthful. That was Patrick Bowler, Fellow of the British Association of Cosmetic Doctors, talking to Mira Sinthalingham about what happens to our skin as we age and how many creams on the market, many of them may not do as much as we hope they do.
So eating and drinking the right things can help us look younger as well as staying out of the sun, but can they actually make us live longer lives? Professor Nick Wareham joins us now. He's the director of the Medical Research Council's Epidemiology Unit at Addenbrooke's Hospital. Now, he's been part of the European Prospective Investigation of Cancer study, better known as EPIC, and in January this year they announced that there are 4 simple things you can do to extend your life by an estimated 14 years. So, Nick, thank you ever so much for joining us. First of all, what are these 4 things that people can do, and why do they have such a large impact on how long we live?
Well, they're smoking, drinking in moderation, not being totally sedentary, so having sufficient physical activity, and eating a diet that's rich in fresh fruit and vegetables.
I guess when you say smoking, you mean not smoking.
Not smoking. Absolutely.
Okay, and so why do they have such a big impact?
Well, they individually, they are risk factors for a whole range of chronic diseases. Indeed, many of the diseases that you were talking with Steve about earlier, cancer, cardiovascular disease. And these are the disorders that really shorten our lives and for which we have evidence that that shortening is modifiable. Now, in the study you're referring to, this is observational data. It's not an experiment. We haven't had a group of people who we've randomized to be smokers or non-smokers. So these are observations in a very big population-based study, but they are robust. And really, what was surprising about the observation is not the fact that smoking and drinking too much are bad for you. It's really the magnitude and it's the scale of the effect on longevity that we observed.
So these are obviously very difficult things to study. You have to rely on people being honest. And obviously, if you get a secret smoker, he could squiff your data completely.
Sure.
But how do you actually study these? How do you try and look at all of these different lifestyle effects? And then it's obviously very difficult to say these people are healthier. It's easy to say these people live longer. So how do you pull all this data together?
Well, what you have to do is that you collect a very big cohort study. So a cohort is a population of people who you recruit at baseline, and you hope that they're free of disease at that point. And you ask them questions, or you may monitor different behaviours. And then you wait, because the key thing is elapsed time. And over time, some people go on to get particular diseases, and some people, unfortunately, die. And in the study that we reported earlier this year, we started out with a cohort of 25,000 people in Norfolk who'd helped us in the beginning of the 1990s, and who were then followed up over time to see who went on to get disease. And really what the essence of epidemiology is that scale, very big studies, and then probability. Because whether or not someone goes on to get disease is a process that involves an element of chance. And clearly some people have certain lifestyles and do very well. Some people may have the same lifestyle and do very badly. But on average, one can estimate the probability of an event occurring. And that's what you do in epidemiology.
So epidemiology is obviously quite a powerful technique. But a lot of people would say, based on their personal experience or anecdotal evidence, they may have an uncle that smoked and drank a bottle of whiskey every week.
Sure.
And lived till 108.
Sure.
So are these people taken account of, or do you try and go for the sort of common denominator? Are you looking at the average, or are you looking at the normal?
Well, we're looking at everybody.
Right.
So for everybody who's got an Uncle Tom who has those characteristics, unfortunately, there's probably an equivalent number of people who have an Uncle Frank who might have, lived an exemplary life in terms of the behaviours we've talked about, but was cut short by disease. So one's looking at sort of average probability. And unfortunately, most people tend to remember the anecdotes that are an excuse for unfavourable lifestyles.
And one of the things that you've been working on is how activity in earlier life affects the likelihood of things like type 2 diabetes or other diseases associated with age. What have you found so far?
Well, physical activity is probably a very, very powerful determinant of many of the diseases that we're seeing rising today, and is clearly a major factor in why, as a population, we're tending to get more overweight. And overweight by itself is the single biggest determinant of type 2 diabetes. I mean, we operate in terms of what's called relative risk in our game. So that's comparing the risk of a disorder in one group compared to a comparison group. And if you were to take obesity as a risk factor, the relative risk is something like 60 for someone who is overweight and obese compared to someone who is a normal weight for type 2 diabetes. It's very, very strong risk factor. And one of the reasons we focus on that is in part because it's an important factor, but in part because it's relatively easy to measure. And the problem about physical activity is incredibly difficult to measure. And we rely on self-report. We ask people about their physical activity. And the bit of activity that people can remember is the part that usually involves putting on Lycra or going to a gym or something very specific and circumscribed like that. In fact, what we're finding is that part is important, but that part doesn't actually occupy much of our life. And most of us spend most of our energy in a rather insensible way, just walking around or standing rather than sitting. And we've been developing techniques for studying that aspect of activity. And it seems that part is really important for determining obesity and diabetes risk. I guess the importance of that is not just as an observation, but what it says about what you should do about the problem. Because promoting sport and encouraging exercise, absolutely critical. But at a population level, probably we need to be also thinking about how do we just encourage people in an insensible way to waste more energy. And that means sort of re-engineering society. It means putting staircases in more prominent positions, perhaps moving escalators and lifts to less prominent ones, things like that.
And so epidemiology is a good tool for informing, I'm guessing, policy, if you can say these sorts of things. So what do you think we should do to try and make our population age more healthily?
Well, I think we should clearly focus on those 4 behaviours as 4 critical public health targets. And I think we've made progress, certainly amongst adults, in smoking. But what's discouraging is the number of children and adolescents who are taking up smoking, because if smoking gives rise to hundreds of thousands of deaths per annum, unfortunately, the smoking industry just has to recruit that number of people to keep their business stable. So I think focusing on the smoking message on people starting is as important a public health issue as trying to help people stop. Clearly, the big furore recently about the moderating alcohol consumption, and that is something that's going up and is a public health issue. Fruit and vegetable intake, there are clearly the 5-a-day messages, and we should really stick to those and try and do our best. Physical activity, in our study, we actually the sort of risk group that gave rise to the risk was actually people who are totally sedentary, who had a sedentary job and who do nothing in their everyday lives in terms of leisure time activity.
Your traditional couch potato.
Yeah, and I guess the message here is that the public health recommendation, which is to do 30 minutes 5 times a week, that's a long way from some people's reality. So I think there's an alternative message, which is actually just do some more, because there are benefits to doing something other than nothing.
Even things like hoovering, which I've been told actually burns quite a lot of calories.
Hoovering, yeah, especially amongst men.
I'm sure DIY as well is bound to...
DIY, anything you can. Actually, very interestingly, we all sit for most of our jobs. And there's a very interesting recent study about the time spent sitting and its relationship to diabetes risk. And, if we've got a sedentary job, there's maybe not much we can do about the total duration of sitting. In the same study, what they looked at was if you break that sedentary time, but overall the sedentary time as a totality is the same, people have more breaks in the sedentary time had a lower risk. And that, I think there may be some important messages there about getting up from our desks and our computers periodically. And I would argue that's probably good for concentration, but it'd be very interesting if it was actually also good for our physical health.
Well, I'm glad to say that the cafeteria in our office is downstairs, so even if we do go and get a chocolate bar, we have to walk back upstairs afterwards. But you said that drinking is going up at the moment. Is it likely that we are storing up problems for the next generation? Are today's adolescents going to be even more disease-prone than today's pensioners?
Well, I think that that is the $6 million question. This is really the problem that we face in public health and epidemiology, because we always use the past to predict the future. So the cohorts that we have now, on which we're basing our information about risk, studies like Framingham or EPIC, those studies recruited people maybe 20, 30 years ago when the risk factors were as they were then, and medical care was different. Yeah. Now, the issue is, what are the current generation going to face in the future? and we don't know. All we can do is say we know that obesity and other risk factors are incredibly important. And based on our observations from the past, we would say that the current generation, if they don't take some action, and particularly with respect to their degree of overweight, are really storing up problems for metabolic health in particular in the future.
Well, that's obviously something we need to keep an eye on, and we shall stay in touch to find out what you find in the future. Thank you ever so much, Nick. That was Nick Wareham from Addenbrooke's Hospital, explaining how some very simple lifestyle changes could actually help us all to live longer, healthier lives.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientist. Now it's time to invite Diana O'Carroll back into the studio for our question of the week. Hi, Diana.
Hello, Helen.
I wasn't here last week, but I hear Chris was saying something rather unkind about your eyebrows.
Yeah, well, no one else knows about his chest dreadlocks anyway. That's a secret we keep here in the studio. Well, talking of hair in places you don't like, how about this question?
I'm Andrew Steer from Cambridge. I was at the barber's the other weekend, and the barber asked the elderly gentleman in front of me whether he'd like his eyebrows trimmed. And he certainly needed it. They were growing quite long. So my question is, why is it that eyebrows tend to grow quite long in elderly people?
So why is it that some men can do that twiddly-twisty thing with their eyebrows?
My name is Professor Desmond Tobin. I'm Professor of Cell Biology at the University of Bradford, where I specialise in skin and hair biology. The hair growth is very susceptible to hormones, to the so-called sex steroid hormones, principally estrogens and androgens. The dominant hormone for males is in the androgen category, particularly testosterone. And surprisingly, the levels of testosterone continue to increase with age up until about the age of 70. So since most of male hair is responsive to androgens, with age and with increasing hormone levels, you tend to get more and more vigorous hair growth, particularly in the areas that perhaps were not as robust when the individual was younger, for example, on their nose and on their ears and on their eyebrows. The nose and the ears have got thousands and thousands of hairs, but they're usually so small you can't see. In fact, the tip of the nose is the hairiest part of your body in terms of density of hairs per unit area. And with time, these can be stimulated with these male hormones, which go up with age and therefore can become more cosmetically visible with age. And the same applies for the eyebrow and for the ears. In women, their estrogen levels drop after menopause, and their lower levels of testosterone, the lower levels of male hormone, then become more engaged with the process of hair growth because they stimulate whereas estrogens tend to inhibit. And you're just releasing more stimulatory power from the androgens that they have.
So, hormones are responsible for the overgrowth of our hairs, wherever they may be. Both men and women have estrogen and androgens coursing through their bodies, but the advance of age is enough to tip the balance and force out these hairs just that little bit. And on another bodily note, this one left me feeling a little sanguine.
Why is it that humans have 3 different blood groups, A, B and O, and do animals have the same blood groupings? Thank you.
So, just what is the point of blood types? If you know why we have them, then let us know by emailing questionoftheweek@thenakedscientist.com or put the answer on our discussion-friendly forum at thenakedscientist.com/forum.
You are listening to The Naked Scientist, and our listeners in Second Life, it seems, have taken on all of the advice that we've given them today, because not only have they all got up from their chairs and started doing exercise in order to avoid being sedentary, but somebody has actually set it to night time so that they're also not getting the ageing effect of the sun. So I'm glad to see that everyone in Second Life is paying attention and learning from what we do.
If only the virtual world had effect on our real lives too. Anyway, now it's time to get back to Ben and Dave, who've been testing out how rubber responds to warming.
Welcome back to Kitchen Science, where just like the elasticity of your skin as you age, we're looking at what happens to elastic bands when you heat them up or cool them down. So Dave has set up an elastic band with a big weight on the end, and we're going to heat that up using the type of heat gun you would use for DIY for stripping paint. We're going to see what happens when we heat it, and then we have Dave's favourite science toy, some liquid nitrogen, and we're going to use the vapour from that to cool it down afterwards. So Dave, it's all set up and the liquid nitrogen is boiling away, so we better get on with it. So Dave, what are we actually going to see here?
Well, normally when you heat things up, they tend to expand. Gases expand quite a lot when you heat them up. Most other materials expand. This isn't necessarily the case with rubber. Now, this is a very subtle effect, so it's going to be moving a very, very small amount. It's very easy to get confused with small movements because your head's moving as well. So I want you to keep your head still by putting it on the table and not moving it. And then move your head so you can sight along the top of the weight something on the other side of the room so you can see any even very, very small movements.
OK, do you promise not to spill any liquid nitrogen on my head?
I'll do my best, Ben.
OK, so I will get my head down to table level. And I'm now leaning on the table. I can see the elastic band and I have it lined up with the bench behind me. Now, Dave is pointing the heat gun at the elastic band. As long as you don't point it at me, Dave, let's get going. Well, I can certainly feel the heat from that. And actually, I can see quite clearly that the elastic band has got shorter. It's lifted the weight up. When we started, it was lined up exactly with the edge of the desk behind it. And now it's a good, well, it appears to be at least a centimetre, if not more, above it. But as you said, Dave, things usually expand when you heat them. That's what I'd expected. So if it gets shorter when you heat it, should I expect it to get longer when you cool it?
Let's find out.
OK, well, I shall assume the position again. And once more, the elastic must have cooled down again now because my head's at the same level and it's back in line with the desk behind it, and you're going to pour some of the vapour from the liquid nitrogen onto the elastic band. Why not the nitrogen itself?
I'm just trying to get it fairly cold, and the vapour is going to cool it down nice and gently.
OK, so it's lined up, and the vapour from the nitrogen is flowing all over the elastic band. Yes, it's dropped by about a couple of millimetres. Really a very small effect, but again, I had it lined up with the desk behind it, and now it's definitely below the level of the desk. So it would seem, Dave, that rubber does exactly the opposite to what you'd expect. When you heat it up, it gets shorter, and when you cool it down, it gets longer. Why does this happen?
Well, rubber is a kind of polymer, and polymer molecules are like huge, great, big, long chains. And now these chains are in a great big mess, incredibly tangled and mixed up. And in rubber, they're occasionally tied together. So it is a bit like a net, like a fishing net, but much more of a mess.
So is this structure, the sort of messy net structure, is this what gives rubber its elasticity in the first place?
Yeah, that's right. When rubber's at room temperature, these long chains can move past each other. They start off all wiggly, and when you stretch them, they straighten out.
But why should it get shorter when you heat it up? Surely, if it's full of lots and lots of these polymer chains, then when you heat them, each of them can expand, and so the whole thing can expand.
Well, the volume of the material probably does get bigger as you heat it up, but that's not the same thing as it gets longer in all directions. I've got a nice little experiment to show you why.
OK, so we have yet another experiment to look at today. Oh, in fact, Dave's got a very long length of chain. Well, I'm assuming this is for securing your bike, Dave.
It comes in handy for various things, yes, Ben.
OK, so you're dangling the chain from your hand down to the floor. So what's this supposed to show us?
Well, if you imagine this is one of the polymer chains, and at the moment it's being stretched out straight, like when we put the weight on it. Now, when you heat something up, you give it more energy, and the energy that a polymer molecule have is basically vibration.
So the hotter the material is, the more each chain can vibrate.
Yeah, that's exactly right. So what I'm going to do now is heat up this polymer chain by giving it a good shake.
At the moment, the very last link in the chain is just touching the floor. So go ahead, give it some energy, Dave. I understand. So now that you're shaking it, the actual bottom of the chain is up around your knees rather than at the floor. So the more energy we put in, the more we can vibrate, and actually the shorter the length of each chain.
That's right. It becomes more wiggly on average, so it has to get shorter and wider.
OK, so that's why heating it up makes the whole thing shorter. But surely once we've got it all stretched out and the chain's already under tension, then surely making it colder can't make it longer in the same way.
Well, room temperature is actually still quite warm by the standards of a rubber molecule, so heating it up is a bit like shaking this chain very hard as opposed to fairly hard.
So cooling it down with the vapours from the nitrogen means that it shakes even less than it does at room temperature, and this actually means that the whole thing can get longer. But that's all the kitchen science we have for this week. Dave and I are going to make the most of this liquid nitrogen and freeze a few things, but we'll be back with you very soon.
So rubber bands are counterintuitive. They get shorter when they heat them up and longer when you cool them down. To read more about this experiment or any of the other kitchen sciences we've done on the show, just go to www.thenakedscientist.com/kitchen science. Or if you're not online, why don't you have a look at a whole load of great experiments in a handy book format? Why not buy Crisp Packet Fireworks, 50 of the best experiments to do at home, brought to you by your very own Chris Smith and Dave Ansell.
A blatant plug there, but we still have Steve Jackson in the studio with us, and we've had a question in from Rebecca, who says, I heard that our cells replace themselves every 18 months, which means our bodies are actually only 18 months old. So how do the cells, the new cells, carry the information about our real chronological age forward into the next generation of cells?
First of all, some cells in our body don't divide, such as nerve cells, and so they really are. They basically last our whole lives. But even the cells that do turn over, that are generated, a new cell is generated from the division of an existing cell. And the age of the existing cell basically gets transferred. The new cell remembers how old the other cell was. And one of the important things that is transferred are the chromosomes. And the ends of the chromosomes, called telomeres, get shorter every time a cell divides and are a very useful counting mechanism. And these telomere shortening is one of the important counting mechanisms that tells our cells how many times they've divided, i.e. how old they are.
Fantastic. Helen?
I've got a quick question here from Rachel in Michigan, and she says, if melanin is responsible for the colour of both my skin and my hair, why is it that the sun makes my skin go dark and my hair go light? Ben, what do you think on that?
That's an excellent question, and she's right. It is melanin that makes both dark hair and it gives the skin your colour. But the thing is that when you grow hair, it's technically dead. So once it grows out of your scalp, all the melanin it will ever have is in that hair. Now, this means that when it gets hit by the sun and broken down by the UV, it means it's gone away completely. Now, in your skin, you have something called melanocytes. Now, these are bits of your cells that create melanin. So when the melanin gets broken down, the melanocytes keep working to produce more melanin. And this is why, in response to sunlight, you get darker, but your hair gets lighter. And I hope that answers your question, Rachel, but I'm afraid that's all we have time for this week. So a big thanks to all our guests, Pamela Bjorkman, Steve Jackson, Patrick Bowler and Nick Wareham. Thanks also to our production team, Diana O'Carroll, Mira Senthilingam, Tom Simpkins and Dave Ansell. And next week, we'll be finding out the latest news from the front line of the war against cancer. We'll suss out the cervical cancer vaccine now being given out in schools across the UK. Dr. Cat will be at the National Cancer Research Institute conference in Birmingham to bring us all the latest news, and we'll find out how you could tweak your own immune system to fight off a tumour. So until the next show, have a great week and goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.